Welcome back to the Deep Dive, where we take on a stack of dense, complicated sources and distill the core knowledge right into your brain.
And today, we are going deep.
We really are. We're tackling the very engine of modern civilization, and I mean that literally. We're talking about thermodynamics.
It's the universal rule book.
Yeah.
I mean, if you want to understand why your car engine is only, what, 30% efficient?
Or why a massive power plant still needs those huge cooling towers.
Exactly. Or even the fundamental limits of rocket propulsion. It all comes back to these laws. You have to grasp them.
So for this deep dive, we've been examining sources that lay out the first and second laws of thermodynamics, the building block processes they describe.
And then the theoretical limits.
Yeah.
The legendary Carnot cycle.
Right through to the brilliant practicality of the Stirling motor.
Mm-hmm.
Our mission today is to move past the textbook definitions and really reveal the simple, inescapable constraints that govern every single energy transformation in the universe.
And to do that, we have to start by cleaning up some very old, very stubborn ideas about what energy and heat actually are. #AdTagR, introduction and establishing the fundamentals.
Okay, let's unpack that immediately. Let's refine our core concepts, because historically, the great thinkers, they were a bit misled, weren't they?
Oh, completely. For a long time, well into the 19th century, the prevailing theory was that heat was this weightless, invisible fluid.
They called it caloric.
Caloric, yes. And it just flowed from hot things to cold things. And, that misconception, it still lingers in our language.
How so?
We say a body contains heat. This coffee cup has a lot of heat in it.
Right. I'd say that.
But the modern definition, the one established by people like Joule, who literally measured the mechanical equivalent of heat, it clarifies that heat is strictly a transfer of energy.
Okay, so it's not a substance, it's a process.
Precisely.
Yeah.
Our sources are very clear on this. Heat, which we write as delta Q, is energy transferred only because there's a temperature difference.
It's energy in motion.
It only exists while it's flowing, like an electric current in a wire. So a body contains energy, yes, but it never, ever contains heat.
Once we get our heads around that heat is just a form of energy transfer.
Well, that leads us straight to the first law of thermodynamics.
Which is, I think, probably the most reassuring law in all of physics.
Reassuring how? Because it just says energy is conserved.
Precisely. It's the big universal law of conservation of energy, just applied specifically to thermal systems. You can't create it, you can't destroy it.
You can only convert it from one form to another or move it around.
That's the rule.
So to apply this rule to a system, let's say the gas inside a cylinder with a piston, we first have to define the energy we're conserving, the internal energy, which we call U.
Right. And U is the total microscopic energy of that gas. So if you could zoom all the way in on the individual molecules.
What would I see? You'd see them zipping around, translating. You'd see them rotating, vibrating. That's all kinetic energy. And U is the sum of all of that, plus any potential energy stored in their chemical bonds. It's the total energy locked up in the system's current physical state.
Okay. So if that's the total energy and we want to change it, the first law says we have exactly two ways to do that. Two independent paths.
Path one is heat, delta Q. You change the internal energy by letting energy flow because of a temperature difference.
You put the cylinder on a stove burner?
Exactly. Delta Q is positive, U goes up. Simple. Path two is work. Delta W. You change the internal energy by mechanical means.
You push the piston down, you compress the gas.
You're doing work on the system. Delta W is positive, and U goes up again.
So the full equation is just starkly simple. The change in internal energy, delta U, is the sum of the heat you add, delta Q, and the work you do on the system, delta W.
Delta U equals delta Q plus delta W.
That looks so simple, deceptively simple.
It is. But it is the absolute bedrock of everything. It tells every engineer, every physicist, what is even possible. You can convert heat into work and work into heat as long as you balance the books and conserve U.
Okay, but before we can build an engine with this, we have to tackle a really subtle but critical distinction. It's about things that depend on where you are versus things that depend on how you got there.
The difference between a state function and a process variable.
This is so important, right?
It's essential.
Yeah.
If you miss this, the whole idea of a closed engine cycle, of getting back to the start, it just falls apart.
Let's use the mountain analogy. I always find this makes it click. If you hike up a mountain, the summit is your final state. When you're standing on top, your height above sea level is fixed. It is a defined value. It doesn't matter if you took a helicopter or the gentle 10-mile path or you rock climbed straight up the cliff.
Your altitude is your altitude.
Exactly. That height is a state function. It only depends on your location.
And internal energy, U, is the thermodynamic version of that height. If your gas has a specific pressure, P, a specific volume, V, and a specific temperature, T, its internal energy, U, is absolutely set in stone.
It doesn't matter how it got to that state,
Not at all.
but the total distance you walk to get to the summit.
Ah, that's different.
That depends entirely on the path. The rock climbing path is short, the winding road is long. That distance is a process variable.
And this is the punchline. Heat, Q, and work, W. They are the distance you walked. They are process variables.
So you can get to the same final energy U by different combinations of heat and work?
Absolutely. You could add a lot of heat and do just a little bit of compression, or you could do massive compression and add almost no heat. Q and W depend entirely on the path you take between state 1 and state 2.
And this is so fundamental, it's even built into the math, into the notation.
Wow.
The sources point this out.
They do. It's a very neat distinction. When you talk about a tiny change in a state function like U, you write it as du, a complete differential.
But for Q and W,
You have to write delta Q and delta W an incomplete differential. It's like a little warning flag in the math.
what's the warning?
The warning is that if you go on a round trip, a full cycle, and you add up all the little du changes, you get 0. You end up at the same height you started at.
Makes sense.
But if you add up all the delta Qs or delta Ws over that same cycle, you do not get 0. You get the net heat that flowed, or the network you did, and that path dependency. That's the whole secret to designing an engine. We manipulate the path to get the biggest network out.
Okay, so we have the rules of the road, we have the first law, and we have this idea of state functions. Now we can start combining them to see how energy moves under specific controlled conditions.
These are the 4 processes, the Lego bricks for building any heat engine you can imagine.
And to make it manageable, we start with a crucial simplification.
The ideal gas. It's an essential tool for analysis. We assume, for a theoretical ideal gas, that the particles are just little point masses that don't interact with each other.
Which means what for the energy?
It means there's no potential energy stored in bonds or attractions between the molecules. The only energy they have is kinetic energy, the energy of motion.
And temperature is just a measure of that average motion.
Right, so for an ideal gas, the internal energy U depends only on its temperature. U is a function of T and nothing else. This makes the math so much cleaner.
Okay, let's start with the simplest case then, the isochoric process.
Isochoric, constant volume, so dV equals 0.
Imagine a thick-walled steel tank welded shut.
Perfect. The volume can't change. Now think about work. Work is defined as pressure times the change in volume.
But the change in volume is 0.
So the work done, delta W, must be 0. The system can't expand, it can't be compressed.
So the first law, delta U equals delta Q plus delta W, just becomes...
Plus delta U equals delta Q. That's it.
all the heat you put in goes directly into internal energy.
Every single joule, which for our ideal gas means it goes straight into raising the temperature. We write it as du equals delta Q, which equals CV times dt. That CV is the specific heat capacity at constant volume.
So this is the most efficient way just to make something hotter. You're not wasting any energy on expansion.
You're not paying any work tax. Correct.
Now let's contrast that with the isobaric process. Constant pressure. dP equals 0.
Right. Think of a cylinder with a piston that's free to move, with the constant pressure of the atmosphere pushing down on it.
So if I add heat to this system, the gas wants to get hotter, pressure wants to rise.
But it can't, because the piston just moves out to keep the pressure constant. The gas has to expand.
And in expanding, it's pushing the piston, it's doing work on the environment.
It is. Delta W equals negative PdV. That negative sign is crucial. It means the gas is performing work, so it's losing energy to the outside world.
So the heat I put in has to pay for two things now.
Exactly. The heat we supply now has to cover two costs. First, the cost to increase the internal energy, du, to make it hotter. And second, the cost to pay for the work done pushing that piston out.
Which means I have to supply more heat to get the same temperature rise as I did in the constant volume case.
You absolutely do. And that leads us to define a different specific heat capacity, Cp, for constant pressure. And Cp is always bigger than Cv.
And this isn't just a vague, it's bigger relationship, is it? This leads to one of the most elegant connections in all of this.
Mayer's relation. It is beautiful. It quantitatively links these two things. For 1 mole of an ideal gas, the difference, Cp minus Cv, is exactly equal to R, the universal gas constant.
Wait, so the extra heat you have to add is exactly the thermal equivalent of the work the gas does when it expands.
Precisely. The difference between the two heat capacities is the work term. The extra heat isn't lost, it's perfectly accounted for as the energy that went into pushing the environment out of the way. It connects the internal molecular stuff, CV, to the external mechanical work, R.
That's incredible.
It is, and you can see it in the numbers. For a simple monatomic gas like argon, it only has 3 directions to move, so its CV is 3/2 R.
Okay.
Add the expansion work cost, R, and you get CP equals 5/2 R. It works perfectly.
And for air, which is mostly diatomic nitrogen, the molecules can rotate too.
So they have more ways to store energy. 2 more degrees of freedom. So its CV is 5/2 R.
And CP would be?
Just add R, 7/2 R.
Yeah.
The work term R is always the same because pushing the piston out is the same mechanical job no matter what gas is inside. The agreement with experiments is a huge win for the theory.
Okay, on to process number 3, the isothermal process, constant temperature. DT is 0. This one is hugely important for engines.
Absolutely critical.
Right.
The key condition here is that the process has to happen incredibly slowly
Why slowly?
to ensure the gas is always in perfect thermal contact with a huge external heat reservoir, like a giant block of ice or a huge flame. That's what keeps the temperature locked in place.
So if T is fixed, and for an ideal gas, U only depends on T.
Then U must be fixed as well. The change in internal energy, du, has to be 0.
So the first law, du equals delta Q plus delta W, becomes 0 equals delta Q plus delta W.
Which rearranges to delta Q equals negative delta W.
All the heat you put in is immediately converted into mechanical work.
A perfect 1-to-1 conversion. And the reverse is also true. If you compress it isothermally, all the work you do on the gas must be immediately rejected as heat to keep the temperature from rising. This perfect conversion is the power source in the Carnot engine.
Which brings us to the final, and maybe most dramatic process, the adiabatic process.
The condition here is 0 heat exchange. Delta Q is 0.
How do you achieve that?
You either need perfect thermal insulation, which is impossible in reality,
Or
the process has to happen so blindingly fast that there's simply no time for heat to flow in or out. A rapid expansion or compression is the practical way to get an adiabatic change.
Okay, so if delta Q is 0, the first law simplifies again. du equals delta W.
All energy changes are purely mechanical.
So if I compress a gas really quickly, like in a bicycle pump,
You put in positive work in, delta W is positive. That energy can't escape as heat, so it has to go into internal energy, U, the temperature spikes. You're literally heating the air with mechanics.
and the reverse is the Sprague effect.
The classic example.
Yeah.
When that pressurized gas expands rapidly, it does work pushing the atmosphere away. It has to pay for that work.
And it pays by taking the energy from its own internal energy, U.
So U drops, and the gas gets intensely cold, sometimes cold enough to form frost on the can.
So in this process, pressure, volume, and temperature are all changing wildly at the same time.
They are, which means we can't use the simple ideal gas law like P times V is constant. That only works if temperature is constant.
This is where we need a new equation. Our sources show a derivation from the first law. It's a differential equation, but we can skip the calculus. What's the result?
The result is the adiabatic equation, which governs this specific path. It's P times V to the power of kappa equals a constant.
Okay, kappa. What's that?
Kappa is the key. It's the adiabatic exponent, and it's defined as the ratio of the 2 specific heats we just talked about. Kappa equals Cp divided by Cv.
And since we already established that Cp is always bigger than Cv,
Kappa has to be greater than 1, always. For air, it's about 1.4. For monatomic gases, it's about 1.67.
and the fact that kappa is greater than 1 is really important when you visualize this.
It's everything. If you plot these processes on a pressure-volume graph, the isotherm is P times V to the power of 1 is constant. The adiabios is P times V to the power of 1.4 is constant. That bigger exponent means the adiabatic curve is always steeper.
Why is it steeper? What does that mean physically?
It visualizes the double whammy of an adiabatic expansion. When a gas expands isothermally, its pressure drops just because the volume is getting bigger.
Right.
But when it expands adiabatically, its pressure drops much faster. Because not only is the volume getting bigger, the gas is also cooling down at the same time. It's losing the internal energy that was helping to prop up its pressure.
So you get less work out for the same change in volume compared to an isotherm.
No, you get a faster drop in pressure.
Oh.
This steepness is critical for how much temperature drops during an expansion stroke, which is essential for setting up the cycle.
Okay, so isochoric, isobaric, isothermal, and adiabatic. We have our 4 building blocks.
Now we can finally build the engine.
So the whole point of a heat engine is to take these different processes and connect them into a closed loop on that pressure volume diagram.
You have to return the system exactly to its starting point. That's the definition of a cycle.
And because internal energy, U, is a state function, if you go on a round trip and come back to the start, the net change in U is
0. Delta U for the cycle is 0.
Which means the net work you get out must be equal to the net heat you put in.
Exactly. And graphically, the network you get is just the area enclosed by that loop on the PV diagram.
You expand at high pressure, doing work on the world. You compress at low pressure, putting some work back in. The area in between is your profit.
And the whole game is to maximize that enclosed area for a given amount of heat input, this quest for maximum efficiency. It leads us straight to the theoretical gold standard.
The Carnot cycle, formulated by Carnot way back in 1824.
Which is just incredible. This was before the first law was even formally stated. He was reasoning from first principles about water wheels and the flow of heat from hot to cold.
And he theorized a cycle that represents the absolute pinnacle of what's possible. A theoretical, perfectly reversible machine.
Perfectly reversible is the key. It means he built his cycle using only the two most efficient types of energy transformation we just discussed.
Isothermal and adiabatic.
Right. The isothermal strokes, where heat is perfectly converted into work, and the adiabatic strokes, where work is perfectly converted into internal energy with zero heat loss. No waste.
Okay, let's walk through the 4 reversible strokes in detail. We're keeping track of the energy, and we're starting at a high temperature, T1, hooked up to our hot source, like a boiler.
Right. Stroke 1, isothermal expansion. The gas expands slowly from point A to point B on our diagram. It stays in perfect contact with that hot reservoir at T1.
So as it expands and does work, heat is flowing in to keep the temperature from dropping.
Exactly. It's absorbing the maximum amount of heat, Q1, and converting it perfectly into useful output work, W1. This is the big power stroke.
This is where we pay for the fuel. We're putting heat in.
Correct. Stroke 2, adiabatic expansion. At point B, we instantly and perfectly insulate the cylinder, cut off the heat source. The gas continues to expand from B to C.
It's still doing work pushing the piston.
It is, but now there's no heat coming in to pay for that work, so the gas has to pay for it out of its own internal energy.
So it cools down.
Drastically.
Yeah.
It expands and cools from the high temperature T1 all the way down to T2, the temperature of our cold reservoir, like the outside air.
So that's how we get from the hot isotherm down to the cold one.
That's the bridge.
Yeah.
Now we're at the cold temperature, T2, stroke 3, isothermal compression.
Okay, so now we have to start pushing the piston back in to reset the cycle.
We compress the gas slowly from C to D.
Yeah.
We're putting work into the system now. And to keep the temperature constant at T2, the energy from that compression work must be immediately thrown away as waste heat, Q3, to the cold reservoir.
We're losing energy here. But crucially, since we're at a lower temperature, the pressure is lower.
Much lower, which means the work we have to put in to compress it is less than the work we got out when we expanded it at high pressure.
Yeah.
That difference is our profit.
Right. And the final step?
Stroke 4, adiabatic compression. At point D, we insulate the cylinder again. We keep compressing the gas from D back to our starting point, A.
We're putting work in, and since it's insulated, that work can't escape as heat.
So it has to go into raising the internal energy. The temperature shoots back up from T2 to T1, and we're right back where we started.
4 strokes, 1 closed loop, a perfect cycle.
And now comes the beautiful part. Let's look at the work. We got work out in strokes 1 and 2. We put work in for strokes 3 and 4. But look at the 2 adiabatic strokes. The work we got out during the adiabatic expansion, W2, is exactly canceled out by the work we had to put in during the adiabatic compression, W4.
They're identical, just opposite signs.
Exactly. CV times T1 minus T2 and CV times T2 minus T1. They vanish.
Wow, okay, so that's a huge simplification. The net mechanical work of the entire cycle comes only from the 2 isothermal steps.
It's just the work from the hot expansion minus the work from the cold compression.
And there's another piece of mathematical magic here, isn't there? Related to the geometry.
There is. Because those 2 adiabats connect the 2 isotherms in a very specific way, it creates a constraint. The volume expansion ratio during the hot stroke, VB over VA, turns out to be exactly equal to the compression ratio during the cold stroke, VC over VD.
And the formulas for isothermal work depend on the logarithm of that ratio.
They do. So now we can finally calculate the efficiency, eta.
Efficiency is what you get out the network, divided by what you paid for, the input heat, Q1.
Right. So we substitute the formulas. The network is proportional to R times T1 minus T2 times the log of the volume ratio. The input heat is proportional to R times T1 times the log of that same volume ratio.
Okay, I see where this is going. This is the moment.
This is a moment. When you divide the work by the heat,
The gas constant, R, cancels out. It doesn't matter what gas you use.
Gone. And because of that geometric constraint, the entire natural logarithm term, the part with the volumes,
It cancels out too.
completely vanishes. All the complex engineering details, the size of the pistons, the type of gas, the compression ratios, they all just disappear from the equation.
Leaving us with what?
The simplest, most profound, and most powerful statement of engine efficiency ever formulated. The Carnot efficiency, eta, is T1 minus T2, all divided by T1.
Or 1 minus T2 over T1.
That's it. It's a constant of nature. The theoretical maximum efficiency of any heat engine depends only on the absolute temperatures of the hot source you're using and the cold sink you're dumping waste heat into. Nothing else.
That's a universal speed limit. The moment you pick your operating temperatures, you've set the absolute ceiling on how much useful energy you can ever hope to extract.
And that formula isn't just an efficiency calculator. It's a statement of impossibility. It's the second law of thermodynamics in disguise. Look at the math. Eta equals 1 minus T2 over T1. What would it take to get 100% efficiency for eta to equal 1?
The fraction T2 over T1 would have to be 0.
Right. And since T1 is some high temperature, that means the cold reservoir temperature, T2, would have to be
Absolute zero Kelvin.
which is physically unattainable. That's actually what the third law of thermodynamics says. Since you can never reach absolute zero, T2 is always greater than 0.
Which means the efficiency, eta, can never equal 1.
Never. A portion of the heat energy taken from the hot source must always be rejected as waste heat to the colder environment. It's an inescapable reality of every engine on Earth, from your car to a star.
This fundamental constraint. This is what formalized as the second law.
Yes, there are many ways to state it, but Kelvin's is very powerful. He said, "It is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work."
Okay, let me play devil's advocate for a second. The ocean is a massive reservoir of thermal energy, trillions of joules. Why can't I build a machine that just sucks in that thermal energy, uses it to run a city, and then just... that's it? I'm not destroying energy. The first law is fine. Why doesn't that work?
Because the first law only tells you what's possible in terms of energy balance. The second law tells you about the direction of spontaneous processes.
Heat only flows from hot to cold.
Naturally, yes. To get work out, you need that flow. You need a temperature differential. If you just have one big isothermal reservoir like the ocean, there's no downhill for the heat to flow. Trying to extract network from it would be like trying to get a water wheel to turn in a perfectly still pond.
So the second law basically introduces the concept of direction, and it rules out what's called the perpetuum mobile of the second kind.
The perpetual motion machine of the second kind.
Exactly.
You cannot just continuously pull useful work out of the ambient environment if it's all at one temperature. You need a hot source and a cold sink. It's an absolute requirement.
And this all leads to the final big conclusion. Carnot's process isn't just some ideal, abstract idea. It is the absolute theoretical maximum. Nothing can be better.
And we can prove it with a really neat thought experiment, a proof by contradiction. It all relies on the fact that the Carnot engine is perfectly reversible.
Meaning you can run it backwards.
Exactly. If you put work in, it acts as a perfect refrigerator, pumping heat from the cold place to the hot place.
Okay, so here's the thought experiment. Let's imagine I invent a hypothetical super engine, M1, and it runs between the same two temperatures, T1 and T2, but I claim its efficiency is higher than Carnot's.
Okay, so we run your super engine, M1, forward. It takes heat from T1, produces some work, and rejects some waste heat to T2. Since it's super efficient, it produces more work for a given amount of heat than a Carnot engine would.
Right.
Now we take some of that work that your engine produced, and we use it to dry a standard Carnot engine, M2, in reverse.
So M2 is now a heat pump or a refrigerator.
A perfect one. It's using the work from your engine to pull heat up from the cold reservoir T2 and dump it back into the hot reservoir T1.
I see where this is going.
If your engine, M1, is truly more efficient, it will produce so much work that after we use some of it to run the Carnot fridge, there will be
leftover work, net work out.
Net work out. But when you look at the heat reservoirs, the Carnot fridge has put all the heat back. The net effect on the reservoirs is 0. So our combined system, your engine plus my fridge, is producing net work while getting it from a single heat source that isn't changing.
We've just built a perpetual motion machine of the second kind.
The very thing the second law forbids, which means our initial assumption must be wrong.
My super engine can't exist.
It cannot. No engine operating between two temperatures can ever be more efficient than a perfectly reversible Carnot engine operating between those same two temperatures. Carnot sets the universal, inviolable efficiency ceiling.
So there we have it. Thermodynamic perfection. A cycle made of two isotherms and two adiabats. But, as engineers discovered very quickly, actually building a practical machine based on the Carnot cycle is, well, it's pretty much impossible.
The technical demands are just insane. Think about it. An isothermal stroke has to be infinitely slow to allow for perfect heat exchange.
And an adiabatic stroke has to be perfectly insulated and happen infinitely fast so no heat can transfer.
You can't build an engine that runs at 3,000 RPM and requires its piston to move infinitely slow and then infinitely fast. It's a non-starter.
So the engineering challenge became, can we find a cycle that respects the laws of thermodynamics, but replaces those impossible strokes with something mechanically feasible?
And that brings us to the Stirling motor. It was actually invented before Carnot's theory in 1816 by a Scottish minister named Robert Stirling.
And what was his clever idea?
He kept the two useful isothermal strokes, but he replaced the two complicated adiabatic strokes with two much simpler isochoric strokes.
Isochoric, that's constant volume.
Constant volume. This design is great because it allows for external combustion. You can heat the engine from the outside continuously.
Okay, let's break down the 4 Stirling strokes and see how they compare to Carnot.
Stroke 1 is the same, isothermal expansion to T1. This is the power stroke. Gas absorbs external heat, kin, and does work. This is where we make our profit.
Then we diverge. Stroke 2 is isochoric cooling.
Right. Here, the main power piston momentarily stops. The volume is held constant. But a separate internal piston, called a displacer, shunts all the hot gas from the hot end of the cylinder to the cold end.
And since no volume change is happening, no work is being done.
No mechanical work. But as the gas moves to the cold side, its temperature drops from T1 to T2, and it has to get rid of a bunch of heat. Let's call it reject.
Okay, stroke 3.
Stroke 3 is again the same as Carnot, isothermal compression at T2. We push the piston back in, putting work in, and the resulting heat, quote, is rejected to the cold sink.
And finally, stroke 4 is isochoric heating.
The piston stops again. The displacer shunts the now cold gas back from the cold end to the hot end. Again, no work is done. But to get back to the starting point, the gas has to be reheated from T2 back up to T1. It requires an input of heat required.
So wait, the heat rejected during the cooling stroke is just CV times T1, T2. And the heat required during the heating stroke is CV times T1, T2.
They are mathematically identical.
That identity, that's the key to the whole thing, isn't it?
That is the central insight. Because without a special component, this engine would be terribly inefficient. You'd have to pay from your expensive external fuel source for all the heat needed in stroke 1 and all the heat needed in stroke 4. It would waste a huge amount of energy.
And this is where Robert Stirling's true genius comes in. This is the invention.
The regenerator. It's a brilliant piece of engineering that solves this fundamental thermodynamic problem.
What is it?
It's typically a porous matrix, something like steel wool or a mesh, or a bunch of fine metal passages placed right in the path between the hot and cold ends of the cylinder. It's a temporary heat sponge.
Okay, walk me through how it works in the cycle.
During stroke 2, the isochoric cooling, the hot gas is forced to pass through the regenerator matrix on its way to the cold side. The matrix absorbs and stores all that heat, reject. The mesh itself gets hot, creating a perfect temperature gradient along its length, from T1 at one end to T2 at the other.
So it holds on to the heat. Then what happens in stroke 4, the isochoric heating?
The cold gas flows back in the other direction, through that same hot matrix, and it picks up all that stored heat required, preheating it perfectly, before it even reaches the hot end of the cylinder.
So the heat exchange is entirely internal. The regenerator stores the heat on the way out and gives it back on the way in.
And if the regenerator is perfect, the external cost of those two isochoric strokes becomes net zero.
Which means the only external heat the engine needs to function is the kin for the main power stroke, the isothermal expansion.
Exactly. And the result of that is just astonishing. When you recalculate the efficiency for a Stirling cycle with a perfect regenerator, the heat terms for the isochoric steps just cancel each other out.
And you're left with
the exact same formula as the Carnot cycle. Eta equals 1 minus T2 over T1.
That's amazing. A practical engine design using simple mechanical strokes theoretically hits the perfect efficiency ceiling of the idealized Carnot cycle. All because of this clever device that internally recycles its own energy.
It's a beautiful demonstration of how clever engineering can get you right up to the limits set by nature. And because it uses external heat, a Stirling engine can theoretically run on anything. Solar power, burning wood, waste heat from another process. It's incredibly versatile.
So, If the Stirling motor is so theoretically perfect and so versatile, why isn't it powering my car and my house right now?
Ah, and that brings us crashing back down to earth, to the reality of irreversibility. The real world is not ideal,
The challenges are in the details.
precisely where the theory demands perfection, heat transfer, and sealing.
You said the regenerator must be perfect. What happens when it isn't?
If the regeneration is imperfect, heat leaks. Reject isn't fully captured, or quired isn't fully retrieved, so you have to buy extra heat from your fuel source. But even worse, heat starts to conduct spontaneously and uncontrollably from the hot end of the engine right down the metal structure to the cold end.
And that uncontrolled heat flow moving from hot to cold without doing any useful work.
That is the definition of irreversibility. It's the primary enemy of efficiency in any real machine. It's a direct loss.
What about sealing?
To get decent power out of them, Stirling engines often need a light gas like helium or hydrogen at very high pressures. And keeping a high-pressure, hot, light gas from leaking past seals is a chronic, very difficult engineering challenge.
So even with a mechanically simpler cycle, the real-world losses from friction, heat leaks, imperfect regeneration, they all add up and ensure that the actual performance always falls short of that beautiful, simple Carnot number. #TagUSive. Outro.
So we've really completed the journey, haven't we? From the first law of thermodynamics, the conservation of energy, which defines what we can achieve,
Right, the transformation of heat into work is possible.
to the second law, which is perfectly encapsulated by that Carnot efficiency. It defines what we cannot achieve.
100% efficiency. It sets that absolute universal limit based only on the temperature difference between our hot source and our cold sink.
And the story of the Stirling motor, with its incredible regenerator, is really the beautiful coda to all this. It's a testament to engineering ingenuity. It shows how we can design practical systems that cleverly manage their own internal resources to get as close as possible to that fundamental ceiling, even if they can never quite touch it.
Throughout this whole discussion, one thing has been clear. Maximizing the high temperature, T1, is the absolute key to maximizing efficiency. In every single modern power plant, every jet engine, the goal is always to run hotter.
Which raises, I think, a really important forward-looking question for you to consider. If the laws of physics have given us the goalpost, get T1 as high as possible, what is the ultimate limiting factor in a modern engine today?
It's not really the pure physics anymore, is it?
Not at all. It's material science. What are the melting points? What's the corrosion resistance, the structural integrity at high temperatures of the alloys, the ceramics, the super materials we use to build turbine blades and combustion chambers?
The ultimate ceiling on the power we can extract from any heat source on Earth isn't just Carnot's formula anymore.
It's the practical strength and temperature resistance of the very materials that have to physically contain that heat. And that is the final, tangible challenge for engineers everywhere.
A perfect place to leave this deep dive. Thank you for joining us as we explored the foundational laws that govern our modern world. We'll see you next time.